it last time. Make an attempt today. So last time we were looking at a variety of properties. Again, in the big picture, what we're trying to do is draw some sort of correlation or some sort of relationship between the wave model of the atom, which is the Schrodinger model, which is based on hydrogen, and then trying to pack more electrons into it to see if it gives us a model that in some way represents experimental results. And so we looked at a couple things last time, and while in a lot of chapters we sort of get done with something and then we don't see it again, a lot of this is going to carry across into the next chapter. So I would encourage you to, there's some things that are more important to keep up with than others. If you don't get the size business straight here, then the next chapter, when we get to lattice energies, is going to be a nightmare for you. So try to keep up with this. So we looked at sizes, and we came up with two trends going up and down. You're occupying different n levels on the periodic table, and so they get larger and smaller as you go up and down. So make sure you know the order there. As you go left and right, we're in the same n levels, but we're increasing the nuclear charge, and that draws the electrons in closer. So when you go from left to right, they get smaller. So those are two trends you should definitely know. And then we related sizes to ionization energies. The ionization energy, even though we use the word ion to refer to a charged atom, in the energy world, the ionization energy is the energy to form a cation. Okay? So what we have then is the first and the second and the third and so on. And there's two sort of things to remember from this. One is the first ionization energy is less than the second, the third, and the fourth, and so on. And the second is trends in ionization energies on the periodic table. Again, that's going to be important to us later on. And let's see, where did that go? There are a couple ways to look at it. This way is very graphical. It shows you pretty clearly that the ones that have the first or the highest ionization energies are in this region of the periodic table, and the ones that have the lowest ionization energies are over here. Okay? So there's an up and down trend and a left and right trend. Again, there's a little bit of funny business here between the nitrogen and the oxygen, and we talked about that a bit, but we're not going to. If you need those values, we will give them to you. And then we talked about electron affinity. The idea here is the energy associated with making an anion. Now, the ionization energy stuff follows very nice trends. The electron affinity stuff really does not follow trends very well when you compare one element to another. But one thing that's always true in electron affinity is the first one's less than the second one is less than the third one, and so on. Again, as the charge builds up on the species, it becomes harder and harder and harder to shove an electron into something that already has a negative charge. So, in the end, what we have are sort of big trends on the periodic table. This one sort of summarizes the atomic size part. This one summarizes the ionization energy, so you can see again, the relationship between increasing size and decreasing ionization energy. Down here, the electron affinity one, I would just suggest there isn't really a good trend. If you look at, in the big picture, these have higher electron affinities than these, but on the other hand, the trend isn't really very good. So you should know what electron affinity is. You should be able to write the equation associated with the first one, the second one, the third one, and so on. But we're not going to focus on, these test-wise, we're not going to focus on trends. Okay, let's see. So the other trend we can look at on the periodic table is what's called metallic behavior. Again, that should be consistent with our idea of how electrons are held inside of atoms. We already know that from before that the metals are over here. So we could ask the question, well, which ones are the better metals? Well, it depends on how you define a better metal, I guess. But there's a couple of ways to look at it. One of the properties of metals is they conduct electricity well. So you could ask which ones of these are really good conductors of electricity. Or we could ask other questions like which ones get oxidized, which ones are easier to oxidize. So the answer to both those questions is essentially the same. If something's going to become oxidized, what does it have to do? Lose electrons easily or gain electrons easily? Remember that was a chapter or two ago? This stuff never goes away. If something's easy to oxidize, it loses electrons easily, right? Which means what? It means those electrons are not tightly held. So the elements on the periodic table that don't hold on to their electrons well should be ones that oxidize easily. Okay? We'll talk a little bit more about metallic bonding in the next chapter, but if something's going to conduct electricity, if we think of electricity as the movement of electrons in this, this wire, then those electrons have to be mobile. So once again, for them to be mobile, they can't be tightly bound to the atoms. Again, those two things usually go together. So the question we can ask is, we take our periodic table, where on the periodic table is it going to be, are we going to find the elements that will most readily give up their electrons? Well, in some ways we've already answered that question, because that's related to ionization energy. Last time we said these guys down here, in this region of the periodic table, give up their electrons relatively easily because they're big atoms. Those electrons on the outer surface aren't held very tightly. The ones that are small, the elements that are small, they're not going to give those up. So if we look at the general sort of picture of metallic trend, we find is the species that are the best metals are in the lower left-hand part, again, we're going to ignore the lanthanides and actinides, are in the lower left-hand part of the periodic table. And the ones that are the worst metals are these guys over here. Okay? So if you're looking for the best metal on the periodic table in terms of conductivity and in terms of its ease of oxidation, you choose francium. Or one of these guys over here, cesium or barium. If those are so good at conducting electricity, why don't we make wires out of them? Why do we use other stuff? Yeah.
They're so rare.
Well, yeah, one, they're expensive, and two, they're really reactive. You try to make a wire out of a barium metal, or rubidium, or strontium, or potassium metal, you'd have a nightmare on your hands, because as soon as it gets wet, it bursts into flames. That's not really a good thing to pack behind a wall in your house. So the reason we use these other metals, like copper, for wiring is not because they're really, really good conductors. They're reasonably good, but because they're good. They conduct and they're also safe. They're chemically inert. But if you're really looking for good conductors of electricity, this is the place to go. So copper's cheap in a relative sense. It's not as cheap as aluminum, which is sometimes used for wiring, but that has some bad effects. But it's cheap and it's relatively chemically stable. So that's the trade-off you have to make. So again, the best in terms of metallic behavior are these guys over here. There's some other stuff in here. We sort of synchronized yesterday with the other folks in the other section. And for the sake of, for a variety of reasons, there's like 3 or 4 slides here about the metallic behavior. And what we're going to tell you to do is just skip those. So this slide, this slide, this slide, and this slide, and this slide, we're not going to do. I know that's terribly disappointing, but okay. So what we want to do now, we've sort of made an argument. Hopefully, you at least moderately agree that for atoms, the wave model with packing all those electrons into atoms gives us experimental results that are consistent with. It gives us results that are consistent with experiments. It doesn't mean the wave model is perfect, because we know it's not. We know that for chromium and copper, for example, we have some issues. But it means it's pretty good. The other thing we want to pursue here is what happens when we try to make ions. If we would take the orbitals for atoms and either put electrons in or take electrons out, will we form the ions that we expect to form? Okay? So let's look at a couple things here. Let's first look at a couple that are obvious. So here's a sodium atom. Okay, so here's the electron configuration for sodium. And if we draw it in the orbital diagram sort of picture, we have 1s2, 2s2, 2p6, 3s1. Okay? So that's a sodium atom. I should put some electrons in there. When we form the sodium ion, what happens? Well, we know sodium forms Na+, so Na goes to Na+, plus an electron, ignoring all the phase stuff. Where are we going to take that electron? We've got a whole bunch of electrons there. Where are we going to take it? Well, again, nature's going to take it from the easiest spot possible, which means the highest energy. So, again, as we go up to higher N levels, then we go to higher energy. So this is the highest energy electron right here. And that's the one that's going to get lost when sodium turns into Na+. And we know that that happens on a regular basis. Sodium metal is really not very stable at all. But we know that sodium ions, like in sodium chloride, are very, very stable. So what's the difference? Well, if you look at sodium as a metal, or as an atom, it's got one electron in that s orbital. If we take that one away, then what do we have left over? Well, what do we have below here? We have a filled n equals 1 level, and we have a filled n equals 2 level. Several times we've seen that if we have a half-filled or a completely filled set of orbitals, that has some stability associated with it that you don't get otherwise. So the fact that we can get rid of this guy, and then our valence orbitals are completely filled, is some level of stability that is associated with that particular cation. So we'd expect the sodium ion to relatively easily give up that electron. If it gives up 1 electron, why doesn't it give up 2? So if this one goes away, and we would form Na2+, where would the second electron have to come from? It would have to come from here. We just got that filled, right? This is sort of like a really stable configuration. If we were taking an electron, we have to take it from there. And that would not be energetically a favorable operation. So once again, what we want to be able to do is when we form ions, typically we end up with a filled set of s and p orbitals. And so you can see that, that clearly happens here with sodium. If we form bromide, okay, what's the deal with that? Well, this is bromine as an atom. And I'm just going to draw the 4p orbitals. So we have 5 electrons there. So those are the 4p orbitals in bromine as an atom. If it just had 1 more electron, then we'd have a filled shell. The p orbitals would be filled. So it relatively readily will pick up an extra electron and then makes a bromide. So you can see if you get sodium atoms in the presence of bromine atoms, that they can pull a swap, they can make a deal. The sodium relatively easily gives up this electron, the bromine readily accepts it, and then they form an ionic compound as a consequence of that. So we can play this game with all the +2 ions, with the -2 ions, and so on. And you'll see that every time you transfer an electron in or out, what you usually end up with when you have anions and cations is a filled shell of some sort. And as we'll see in the next chapter, that's sort of the thing we're always after when we look at stability. This is a picture we've seen before. So if we look at the cations, or the alkali metals here, they lose an electron, and when they do that, they become isoelectronic with the noble gases next to them. Okay, so sodium over here contains 11 electrons. It loses 1, it has 10 electrons like neon, and then that's a stable configuration because the s and the p orbitals are filled. Fluorine becomes fluoride and becomes like neon. So again, that term we used before, isoelectronic, means it has the same number of electrons. But what's really more important than the same number of electrons is it has the same electron configuration. So the electron configuration for neon is the same as for fluoride and for sodium ions. And so once again, you can sort of extrapolate that. Oxygen If it loses 2 electrons, it becomes like neon. Magnesium, I'm sorry, it gains 2. And magnesium, if it loses 2, becomes like neon. So once again, the target for these things when they form cations and anions is to try and become isoelectronic with the neutral gas that's closest to them. All right, we'll talk about let's talk about sizes of these, and then we'll come back and talk about transition metals. So what I told you in this stuff really applies to these elements and these elements. We'll talk about the transition ones in a minute. But while we're on these other guys, let's jump ahead and talk about size. And then we'll come back to the transition metals. So, again, the wave model lets us predict the charges, the appropriate charges, when we make cations and anions. What about sizes? What do we think should happen here? What we really want to be able to do is compare sizes of things. So if we have a bromine as an atom, or a bromide as an anion, or here we have a sodium and a sodium plus, what we'd like to be able to do, or we should be able to do, based on the wave model, is predict relative sizes, and then look at these experimentally and see if it follows. So, let's see. Let's take these 2 guys first. Which one's smaller? Sodium as an atom or sodium ion? What do you think? Well, when you're looking at sizes, what are the 2 things you have to consider? What's the nuclear charge? And how many electrons are there? And where are they? So, does nuclear charge really matter here? We're comparing this one to this one in terms of size. Does the nuclear charge really matter? It's the same for both. So that's almost irrelevant. Okay? But what is different? How many electrons are in the sodium atom? The sodium's atomic number 11, so we got 11 electrons, right? In a sodium ion, we have 10 electrons. How does that answer the question for us? What do those electrons on the outer surface of the species do? They attract each other? They repel each other, right? So if I have a sphere and I put 10 electrons on its surface, all those electrons are repelling each other. If I put 1 more electron there and then I have 11, they're going to repel each other even more. I'm adding more repulsive terms. The more repulsive terms you have between all the electrons, the larger it is, because it causes it effectively to swell up. So this one, meaning sodium as an atom, is larger than sodium as a cation. Now we can even make a better argument. So just based on electron counts, that would be the case. But there's another argument we can even throw in here that actually makes it better. Sodium as an atom has an electron in the n equals 3 level. Sodium ion has its outermost electrons in the n equals 2 level. The n equals 3 levels further away from the nucleus, so it's bigger. Okay, so there's a variety of ways you can approach this from when you look at the answer here. So once again, the neutral species is always going to be larger than the cation. What about bromine and bromide? So once again, does the nucleus matter? Same nuclear charge, right? How many electrons do we have in bromine? 35. So here we've got 35 electrons with the same nuclear charge, and here we have 36 electrons with the same nuclear charge. Same argument. If we have more electrons on the outer surface of this sphere, they're going to repel each other. So that's going to cause that thing to expand to try and minimize the repulsive interactions between the electrons. And you can make that argument for any time you compare an atom to its anion. The anion is always bigger. So as a general trend that you can always follow and always use, for the same nucleus, so that means for the same element, for the same nucleus, the cation is always going to be the smallest species. Okay, so if I have some arbitrary species X as an atom, X plus is always going to be smaller than X. and X minus is always going to be larger. Okay? Again, it's just because of the number of electrons that are repelling each other. What if we drag things with multiple charges? What do you think? So, if I put X2 minus, where would that go? It'd be kind of hard to make this, but if you could make that, how would you do it? You'd have to stick another electron on it, right? So you get 37 electrons. More repulsive turns, it gets bigger. So X2 minus is less than X3 minus, and so on. Same argument in the other direction. The larger the cation charge is, the smaller it becomes, because you're taking away those repulsive turns. So this sort of general trend here, which is written in the opposite direction, but the inequalities are in the other direction, pretty much tells you which ones are larger and which ones are smaller. Anions are always larger, cations are always smaller. So how do we experimentally measure this? I mentioned to you last time we talked about covalent radius and what that means. So how do we know experimentally if we have X, let's say it's sodium, and then we have Na plus, how do we measure that? Well, the way you measure the cation size is you get an ionic solid. In this case, this could be sodium chloride. If these are sodium ions and these are chloride ions, then you take the distance between them, and somehow you have to partition the distance between the nuclei to part of it going to the anion and part of it going to the cation. So you have to know the sizes of a couple of these, and then you can do the rest of them. But it's the same concept. You always measure from nucleus to nucleus. And the reason we do that is because that's the only thing that we really know where it is. The electrons are just outside of the nucleus, and so you can't really make a measurement there. So experimentally, if you do that, you can determine the sizes of cations and anions on the periodic table. What do we end up with? So, let's see here. These are the anions. And so the red that's on each one of these is the size of the atom. Okay? So if we look at fluorine, that's the size of a fluorine atom, the red side. And then fluoride is the other part of this. You can see it's larger. So every time we have a -1 charge for the halogens here, notice the anion is larger than the neutral atom. Okay? And if we look at oxygen and sulfur, we form the -2 ion. Look at the size of sulfur -2. It's significantly, almost twice as large as sulfur atom. So as you start to make anions out of these, they can get really large. They can almost double the size in some cases. And it really, you wouldn't think and expect, I've added 2 electrons and it causes that big change. But again, that's just experimentally what happens. If we form cations, it goes in the other direction. So the purple or blue or whatever color that is the size of a sodium atom. And if we take that 1 electron away to make sodium ion, then it becomes the gray on the right-hand side. Notice that is significantly smaller. In most cases, it's a lot smaller. So cesium becomes much smaller when it becomes cesium ion. And again, typically over here, the reason for that is because you're taking away an electron in a higher energy orbital, and what you're left with is an n level that's 1 less. Okay? So that's closer to the nucleus. So you can also see the trend here. If we have, we form +2 ions, for example, with strontium or calcium, that +2 ion is much smaller than the atom itself. So the sizes of ions and the sizes of atoms are different. And what we're going to need in the next chapter is to be able to look at a cation or an anion and be able to predict their relative sizes. Okay, so we did stuff with forming anions and cations with these elements over here. So fluorine goes to fluoride, sodium goes to sodium ion, and so on. If we start to look at making cations with transition metals, it's going to look like our wave model of the atom doesn't work. things don't work quite the way there that we would expect them to work. So let's take an example. Let's look at iron. Okay, so let's write down the electron configurations for iron. So iron is going to be right here, so we can do this with the noble gas configuration. It's going to be argon, and then what? So argon takes care of those 18 electrons, and then what? Well, then I gotta come over here and go 4s2. 3d what? How many d electrons does iron have? 6, okay? Once again, that's the second number in the atomic number. So that's the electron configuration. And if we draw that in sort of an orbital diagram like we did before, following all the rules we saw before, 4s2, then we end up with this. Okay, so we predict a couple things about iron. Okay, so we predict one, it's paramagnetic. It's got unpaired electrons. We'll look in a minute here and see how you can measure that. That's relatively easy to do. And the second thing we predict is if we form iron plus 2, so we take iron and oxidize it to iron 2 plus 2 electrons, where will we predict those electrons come from if that's our orbital diagram? Well, if we follow the rules, we should take the electrons from the highest energy orbital, right? So if we're going to take 2 electrons, we should take 2 of these d orbitals, or 2 from these d orbitals. If you look at that and do that experimentally, you find that's not where they come from. Those electrons, when you take 2 away from iron, do not come from the d orbitals. They come from s orbitals, particularly the 4s. So does that mean all this stuff we've done so far is useless? Because this ordering appears to be wrong. Well, it's not really wrong. It's just that the model that we're using, when we fill these orbitals up from bottom to top, the model we're using is for a hydrogen atom, which has 1 electron. Iron has 26 electrons. As you start to put electrons into that model, the orbital energies start to fall. And they don't all fall at the same rate. So what happens here is shown in this picture right here. So this blue line is the energy of the 4s electrons. And so what you'll see is when you're here at atomic number 1, which is hydrogen, in the hydrogen atom, the 4s orbitals are higher in energy than the 3d orbitals, which is the green one. As you start to put electrons into there, so you put 1 electron in, 2, 3, 4, all the way up to 26, then notice that the energies of these orbitals start to fall, but they don't fall at the same rate. So by the time you get over here to atomic number 20, which is calcium, and then you get to 21, which is scandium, right here, when you get over here, then the energy of the 3d orbital is actually less than the energy of the 4s. Okay? And again, the reason for that is well beyond what we do in this class. It's an observation. That's what experimentally is measured. But it comes from trying to put too many electrons into an atom that was designed for 1. So again, there are limitations. So this really isn't the correct picture for an iron atom based upon ionization. So when we look at the orbital or the electron configuration of iron 2, we don't take those orbitals or those electrons from the d orbitals, but rather we take them from the s orbitals. So transition metals, when you form ions, the first electron comes from an s orbital, the second one comes from an s orbital, and the third one comes from a d orbital. Okay? So I added some stuff this morning. I don't know what happened to the slides. So this little business at the bottom here I added this morning, and I re-uploaded the slides to Blackboard, but if you printed these and you don't have this on the bottom. So when iron goes to iron 2, we have this electron configuration, argon 3d6. And when it goes to iron 3, then we have to start taking it out of the d orbitals. Okay? In in Chem 2, when you do the chapter on transition metals, then you'll come back and revisit this. But in transition metal ionization, the first electron comes from the s orbital, the second from the s orbital, and after that, then you have to start taking from d orbitals. So once again, it's another one of those exceptions to what the wave model of the atom is. But it's really unavoidable since there's so many electrons. All right, so that's the electron configuration for silver. Okay, so how do we know if we have unpaired electrons? We said it's paramagnetic. How do we know that? How do we measure that? Well, actually, the experiment is really easy. This is done. This is a physical picture of a balance. There's electronic ways to do this now. But each one of these little unpaired electrons acts like a little bar magnet. So here's the experiment you can do. You take your sample. Now this says this one's diamagnetic, but let's just pretend we don't know. We take this sample and we put it on a balance, and let's forget the magnetic field is here right now. And so you get this beam is parallel or horizontal, and so whatever the mass is over here is the mass of this. Okay, that's the balance principle. So now what we do is take and put a magnetic field around that sample. If that sample does not interact with the magnetic field, then the balance stays horizontal. Okay? That would be the case if this substance right here was diamagnetic. So remember, diamagnetic means all of the electrons are paired. We have spin pairs everywhere. If we have unpaired electrons, like we do in the case of iron here, then those unpaired electrons interact with this magnetic field. And what was a horizontal beam will shift, and what happens is these unpaired electrons get attracted into that magnetic field. So it will shift, and instead of being horizontal, it'll pull it down, okay, towards the magnetic field. And then you can rebalance it by adding some mass over here. And the amount of mass you add over here is proportional to the number of unpaired electrons. So if we have one unpaired electron, you'd add 1 unit of mass. If you had 2 unpaired electrons, you'd have twice that amount of mass. So it's relatively easy to do this. You need a really sensitive balance, but if that's easy to get. So it's not hard to measure these things. And what this doesn't tell you is that these electrons are unpaired in a d orbital, for example. There's other ways to do that. So again, it's not an expensive experiment to do. If you've done that, but you haven't, you probably never will. But it's a tedious measurement because it's a very it's a very small amount of mass that causes that to happen. Okay, so what we've got then, by the end of this chapter, is again a way to look at and put electrons into orbitals that were designed for a hydrogen atom when we have more than one electron. In some cases it works really well, in some cases it doesn't. Copper doesn't work particularly well, chromium doesn't work particularly well. The transition metals, when we do ionization, doesn't have some issues. But as long as we know what those exceptions are, then we can still continue to use that model if it predicts experimental things relatively well. The reality is, even this was done. Let's see. Bohr came up with the Bohr model of the atom in the early 1900s. The multi-electron atom was really sort of tinkered with in like the mid-1900s. So it's been 50, 60, 70 years, and the model of the atom today still doesn't know how to handle multiple electrons. So we can do one of two things. We can either pack up and go home and just say, well, we don't have a model, we can't study any more chemistry. Or we can try and use this one and just recognize that there are limitations and try and make some progress and understand molecules. Well, clearly we're not going to pack up and go home. So what we're going to do is take that model, as imperfect as it is, and see if we can figure out how these imperfect models for atoms can give us models for molecules. Again, in the end, we're going to have some issues, but we'll try and do the best we can. So the next chapter is really kind of a continuation of this one, where we take these sort of pictures and try and make molecules. All right, so what are we going to do here? We're going to go back and sort of review some things that we did earlier when we talked about what an ionic bond is, what a covalent bond is. And then what we will do is separate those and look at them individually. So we'll look at ionic bonds. And that's really not a big deal because that's just a Coulombic interaction between two charged particles. The covalent bond is going to require some more work and some more thought. And when we're done with those two, we're going to recognize that neither one of those two is perfect, and there's a lot of stuff that's sort of in between. And the stuff in between is usually more interesting than the stuff that's on the edges. So we'll then go back and look at some more thermo, and again, talk about the stuff in the middle. So let's just do a quick review of stuff that hopefully we remember from before. So we take our periodic table and break it into 3 different regions: nonmetals, metalloids, and metals. Okay. These are the guys that form anions. Now we know why. These are the guys that form cations, and now we know why. These metalloids don't really readily form cations or anions. If you look at that, you say, well, why wouldn't they? Well, in order to form a cation, it's got to lose enough electrons to take on a noble gas configuration. So if we looked at, say, boron, if it's going to have a noble gas configuration like neon, it needs to lose 1, 2, 3, 4. It needs to lose 5 electrons. That's a lot of electrons. It's not going to happen. On the other extreme, if it's going to form a cation, it has to lose, 1, 2, 3 electrons. Again, that's possible, but on a tiny atom like boron, that's not going to be very energetically favorable. So you generally don't see these things forming cations and anions because they would either have to gain too many or lose too many. The ones that form cations and anions are typically the ones that are sort of like right on the border. 1 electron changes are common, 2 electron changes are common, 3 is less common, 4 is really almost unheard of. It does happen, but not very often. All right, so we have talked about the different kinds of bonding, but let's again make sure we're on the same track. In ionic bonding, let's do this with pictures as opposed to words. So in an ionic bond, we form that because we have an electron transfer of 1 or 2 or some number. In this case, we've gone through that several times. Sodium ion loses an electron, gives it to a chlorine atom. That becomes sodium ion, chloride ion. They're close to each other. Electron transfer happens like when they're right in contact with each other. Electrons don't transfer long distances. And so they're right next to each other. So the obvious thing that's going to happen there is the cation and anion are going to stick together. And so that happens many times, and you get an ionic solid that looks like that. Notice how the relative sizes of these things change. Sodium atom is really pretty large, and the sodium cation is really small. Okay? So when we look at sodium chloride like this, what we have to do is remember that we need to look at the size of the cation and not the size of the atom itself. Covalent bonding, again, what we're going to look at is sharing of electrons. No one atom in a covalent bond steals electrons from the other. Somehow they work out some sort of sharing agreement or some arrangement so that 2 electrons between these two act as essentially the glue that holds them together. All right, we'll talk more about that when we get there. We're not really going to do much with metallic bonding, as I told you before, but it's here just so you can kind of see how it's different than the other two. In the case of metallic bonding, we have a whole bunch of electrons, and the electrons don't really belong to any nucleus at all. They kind of belong to the whole solid. So sometimes this is called the sea. It's considered to be a sea of electrons. You just have this, this mass, and you have a lot of mobile electrons that are in there. So an electron that's in this sample of sodium doesn't really belong to any individual atom. That becomes really difficult to build a model for, and that's one of the reasons that we're not going to spend much time on it. These two we can build models for and try and understand in terms of the kinds of atoms that we have. This is kind of an intimidating picture, but the point here is if we have three kinds of bonding, covalent, ionic, and metallic, then we have things that are clearly in one of those three categories. But we also have, you should really think of this, we're going to focus on this axis right here. You should really think of bonding as sort of a continuum between being purely ionic and purely covalent. We will look at things that are purely covalent, chlorine, Cl2, bromine, Br2. Those we can claim are purely covalent. But there's other things that have a little bit of character that's covalent, a little bit that's ionic. So we really have a continuum along here. And so as we look at this, what we're going to do is look at this first and pretend like it's the only thing in town. And then we'll look at this one and pretend that's the only kind of bonding available. And then we'll look at the stuff in the middle. The stuff in the middle has some characteristics of both, which makes it obviously much more difficult. All right, so how are we going to do this? Well, I don't know about you, but at some point it gets really tiring when you want to know the electron configuration for something or how many electrons there are. They keep doing 1s2, 2s2, 2p, whatever. Okay? What we'd like is some sort of notation so that we can just look at it and know these are the electrons that are in the valence shells of this atom, and these are the electrons that are going to be involved in bonding. I don't want to have to draw these pictures all the time, as nice as they are. There's just at some point, if I'm interested in bonding, I don't want to have to do this. I'd rather just look at something that tells me, here's how many electrons I have to make bonds with other things. And a guy named Lewis came up with a scheme here, so this is called the Lewis dot structure. This is the same Lewis, let's see, I think we mentioned Lewis acids and Lewis bases as types of acids and bases, but we didn't do anything with them. You'll do that in Chem 2. So this guy's name shows up several times between Chem 1 and Chem 2. He came up with a relatively simple scheme. Again, it's not perfect, but it works really well. So that we can just look at an atom and using a couple dots, I use X's on the board because dots sometimes don't show up well. Using a couple symbols, we can just look at that atom and we can know immediately how many electrons that particular species has in order to interact with other things. Okay, so let's look at nitrogen. So all of these are examples of what are called the Lewis dot structure for the nitrogen atom. So the scheme for the general template here is you take the element, whatever it is, and we're primarily focused on S and P orbitals. So in this class, we're primarily focused on how does the bonding occur between atoms when you look at the S and the P orbitals and the electrons in those on other atoms. So if X is a generic sort of any element you like, and we're interested in the electrons that are in the S and the P orbitals, and it doesn't matter what the n level is, how many electrons do we have to account for? So in S orbital, we put how many electrons? Maximum capacity is what? 2, right? In P orbitals, the maximum capacity is 2 per P orbital. There's 3 P orbitals, that's 6. So we have to account for 8 electrons. And we're always interested in whether they're paired or not. So you never draw the rectangular boxes. But around each symbol, there's a sort of an imaginary rectangular box. And in that box, you can use dots to represent the electrons. Okay, so if we look at and take the case we got up there as nitrogen. Nitrogen has 7 electrons. Notice that there's 5 dots on all these. Why don't we have 7 things? So if you do the electron configuration for nitrogen, it is 1s2, 2s2, 2p3. Okay? So when we put the electrons in the box around nitrogen, we end up with 5. What does that tell you we're doing there when we look at all the electrons that are available in the nitrogen atom? Which 5 are we interested in? We're interested in the 5 that are in the highest n level. We don't care about the 1s electrons. when species form bonds with other stuff, they always use the highest energy orbitals. So these 5 dots in a nitrogen atom represent the 5 electrons that are in the n equals 2 level. The n equals 1 level, we know it's there. It doesn't have any effect on bonding or interactions with other things at all. Okay, so what I'm going to tell you for this class is, so we've got 1 s orbital and 3 p orbitals, right? As far as I am concerned, there's no notation that says, well, this would be the s orbital and these 3 would be the p's, or this is the s. It doesn't matter. Now, somebody, I don't know what rules they're going to give you in lab, so that's why I'm very carefully, I don't want to confuse one with the other. If they give you rules about how you should put electrons in these boxes in lab, you got to follow their rules, because they're going to, they're going to grade your labs. But I'm telling you in here, from my point of view, this and this and this are all the same things. I can look at any one of those and I can tell 2 things. One, I can tell that nitrogen has 5 electrons that it can use to interact with other things. And I can also look to see that 3 of those electrons are unpaired. Okay? So we got 1 pair here and 3 unpaired. If you look at what we've got here, that's consistent with that. The reason I don't care, and the reason it doesn't matter, is when atoms form molecules, all the electrons go into the pool of the molecule. So when we make a nitrogen molecule, we'll see later on how you get to this. All of the electrons that are involved in that nitrogen molecule are in the molecule. They have no idea whether they came from this nitrogen atom or this nitrogen atom. Right? Electrons don't have memory. They just exist. And so, from that point of view, it makes no difference whether we use this picture or this picture or this picture. The important thing is we have 5 electrons. Okay, so that's just all the rules. So let's look at how this works out in terms of elements in the periodic table. If we look at, so here's our nitrogen picture. If you look at the other elements on the periodic table, you'll see that you have different dot configurations based upon how the electrons are arranged. So here's oxygen, so we've got 1 more electron. Obviously we have to start pairing. Fluorine looks like this. And here's the noble gas neon. This is kind of a special configuration. Okay? That's called an octet of electrons. So octet meaning 8. Why is that special? What have we filled there? What orbitals have filled? Well, we filled the s orbital and the p orbitals. They're completely filled. Remember? That's a stable configuration. So when we see this picture right here, or this for argon right here, we have to think that's a special configuration. We have 8 electrons. We have 4 pairs of electrons. We have an octet. And that has some stability associated with it that's not present in all these other pictures. So when we make molecules and when we make ions, our target, our goal, is going to be to take these atoms, which do not have octets of electrons, and combine them with other atoms, so that in the end, we get an octet of electrons on everything. Except for what? You've done this before. What's the exception to the octet rule? Hydrogen. Hydrogen doesn't want an octet. You can't take 8 electrons and stick it around a hydrogen atom. Okay? So what's hydrogen going to want? Hydrogen's going to be happy with 2. So we'll deal with hydrogen later. But octet is sort of the magic thing except for hydrogen. Again, if you look at these, you'll see that as you go up and down in a column, the dot structures are exactly the same. Shouldn't it be that way? If you look at carbon, it's got 4 electrons in the n equals 2 level. If you look at silicon, it has 4 electrons in the n equals 3 level. So if you know the dot structures for any element, you also know the dot structure for all the elements below it in the periodic table, which makes it really easy to predict reactivities. If I look at the reaction with carbon, the reaction with silicon are almost the same, because it's the same dot structure. All right, so next time what we'll do is see how this relates to ionic compounds and we'll look at some properties.